black, a silence so deep it seems to press inward, as though the very absence of sound has weight. Then a faint wash of light, not bright, but ancient, like the ghost of a fire long extinguished. It is the shore of the observable universe, the limit to which our eyes, our instruments, and our physics can reach. Here, the first light ever born still drifts, stretched thin by the slow breathing of cosmic expansion. It is the faint afterglow of the Big Bang, a whisper from nearly 14 billion years ago. From this shoreline, the universe does not end. It only recedes into a darkness our telescopes cannot pierce, an endless ocean of space-time where the waters are made not of atoms, but of the very geometry of reality. Suspended within that ocean, like the ribs of some cathedral without walls, runs the great cosmic web, threads of galaxies, dust, and dark matter spanning hundreds of millions of light-years. Between those threads are hollows so vast that even light, moving at the ultimate speed, would take eons to cross them. They are the silent cathedrals, cosmic voids, not empty in the way a room might be empty, but empty in a way that rewrites the meaning of absence. Some stretch hundreds of millions of light-years, containing only a scattering of dim, lonely galaxies, and yet, from their quiet arches, they shape the fates of clusters, dictate the motion of superclusters, and may even hold the key to the universe's accelerating expansion. Here, in these halls of darkness, the universe reveals an architecture built as much from nothing as from something. The question that remains is that nothingness, merely the space between, or something far more profound. Long before humanity learned to navigate the sea of stars, it charted the oceans of its own world. Sailors traced coastlines, explorers sketched continents, and the known world expanded like ink spreading across paper. In time, the empty spaces, on those maps the vast blank regions marked only by dragons and guesswork, shrank away under the weight of observation. Astronomy had its own age of exploration. The invention of the telescope in the early 17th century transformed the night sky from a scattering of points into a textured realm of worlds, nebulae, and galaxies. But for centuries, maps of the heavens remained flat, like the old maps of Earth, beautiful but without depth. Stars and galaxies were positioned by their coordinates on the dome of the sky, yet their true distances, the third dimension of the cosmic landscape, remained elusive. By the middle of the 20th century, the tools to change that were finally at hand. Spectroscopy allowed astronomers to measure the redshift of galaxies, the stretching of their light by the expansion of the universe, and thus to estimate how far away they lay. For the first time, it became possible to build a three-dimensional chart of the universe. The age of cosmic cartography had begun in the late 1970s. At the Harvard-Smithsonian Center for Astrophysics, two astronomers, Margaret Geller and John Huckra, set out to construct one of the first comprehensive 3D maps of the universe. Their project, known as the CFA Redshift Survey, would record the distances to thousands of galaxies. The work was slow, meticulous. Night after night, telescopes gathered faint spectra from galaxies so far away that their light had begun its journey. When dinosaurs still roamed the Earth, each spectral line measured was a marker in space, another pin on the invisible scaffolding of the cosmos. Geller later recalled the strange intimacy of the process. Each dot of light on the photographic plates was not just a star, but a vast island of hundreds of billions of stars, frozen in time. And yet, their positions were not random. As the data accumulated and the first slices of the map emerged, a remarkable pattern took shape. Galaxies clustered together along immense chains and sheets, leaving behind vast regions where almost nothing could be found. One of the most striking was the Great Wall, an enormous sheet of galaxies stretching over 500 million light-years. But beyond these glowing chains was something stranger still. The Boats Void. Located in the direction of the constellation Boats, this void was unlike anything they expected. Spanning nearly 330 million light-years in diameter, it contained only a few dozen galaxies, a number so small it seemed almost absurd. In a universe already vast, the Boats Void was a chasm of near-total absence. Light would take hundreds of millions of years to cross it, and a spacecraft traveling at the fastest speed imagined by humanity would still be adrift in darkness for hundreds of generations. We expected clumps and gaps, Geller would later say, but not this, not an emptiness so vast. When the results were first presented, many in the astronomical community reacted with caution. Could this apparent emptiness be an artifact of incomplete data? Perhaps the survey had not yet captured the faintest galaxies. Some suggested that instrumental limitations might have erased whole swaths of faint light from the map. Yet as more surveys followed, each with better sensitivity, broader coverage, and deeper reach, the void did not vanish. Instead, it grew sharper, its boundaries better defined. Other voids began to appear, scattered throughout the cosmic web, each different in size, but united in their eerie absence of matter. The skepticism gave way to acceptance. The universe was not a smooth distribution of galaxies. It was a vast web of filaments and clusters, with most of its volume occupied by these yawning voids. In time, the emerging maps began to resemble an intricate lacework, or the foam of a breaking wave frozen in place. Filaments of galaxies formed the bright edges of immense bubbles. Inside each bubble was a hollow region, a void sometimes, hundreds of millions of light-years across. The structures were so large that the human mind strained to comprehend them. Imagine a sphere that could hold the Milky Way and thousands of other galaxies, and yet be almost entirely empty. The scale dwarfed even the largest known galaxy clusters. This was the shape of the invisible, the architecture of the universe, on its grandest scales. The cosmic web was both a map of presence and of absence, and in its absences lay the greatest mysteries. The discovery of the voids was not just a curiosity, it marked a profound shift in cosmology. For decades, the cosmological principle had held sway, the assumption that, on sufficiently large scales, the universe was essentially uniform. The voids challenged this idealized vision, while the principle still held, in a statistical sense, averaged over immense distances. The universe's matter was evenly distributed. The reality was far messier. Matter was concentrated into an interconnected network, with the voids dominating the space between. It was as if the universe were a cathedral, its stonework composed of galaxies, its sweeping arches made of nothing at all. In the years following the CFA survey, astronomers began to realize that the voids were not merely empty spaces between the important structures of the cosmos. They were an integral part of how the universe had evolved. The expansion of space, the clustering of matter, and the distribution of galaxies all seemed to be shaped, in part, by the silent gravitational influence of these hollows. The Boats Void, once thought to be an anomaly, was joined by an entire menagerie. The Sculptor Void, the Local Void, the Eridanus Super. Each one, in its own way, deepened the puzzle. Why were they so large? Why were they so clean? And could their existence tell us something about the very forces shaping the universe? The first maps had been drawn. The coastline of the cosmic shore was no longer a smooth, featureless curve. It was jagged, full of gulfs and bays carved from space-time itself. And somewhere, beyond the reach of those early maps, other voids waited to be discovered as the 20th century gave way to the 21st. Technology would begin to illuminate the voids with unprecedented clarity. Satellites would chart the faintest whispers of cosmic radiation. Telescopes would trace the delicate filaments that wove between hollows. Supercomputers would breathe digital life into the growth of structure from the Big Bang to the present. And yet, the more clearly we saw, the deeper the mystery grew. For inside the voids, these silent cathedrals of nothingness, there were hints of forces that might shape the destiny of the entire cosmos. The age of maps was over. The age of questioning had begun. For most of modern cosmology's history, a simple principle had provided comfort in an otherwise overwhelming universe. On the largest scales, matter is evenly spread. This was the cosmological principle, the idea that no matter where one looked, or from where one looked, the universe would appear the same. It was an elegant assumption. It made the equations of general relativity tractable. It gave order to the chaos of an expanding cosmos, and it matched, at least in broad strokes, the early observations of the night sky. Galaxies scattered across all directions, like seeds, on a limitless field, but the voids were a rupture in that serene image. Their sheer scale and emptiness were not just statistical fluctuations. They were immense regions where the matter density plummeted to a fraction of the cosmic average. It was not the quiet variation of a gently uneven field. It was the deep chasm of a canyon carved into the very fabric of space. Here was a new architecture, not a smooth universe, but one built like a vast cathedral with towering pillars of galaxies and between them sweeping naves of darkness. The principle still held in a purely mathematical sense. Average enough of the universe and uniformity would emerge. But the reality, laid bare by surveys, was intricate, uneven, and startlingly empty. Numbers can dull the mind, but here they stagger it. The boat's void spans 330 million light-years across. That is nearly 3,000 times the diameter of our own Milky Way. Imagine the Milky Way at the center of that darkness, its spiral arms, its hundreds of billions of stars, and then imagine a journey outward in every direction. After 2 million light-years, you would leave the galaxy. After 10 million, the local group would be behind you. But for hundreds of millions of years of travel at light speed, you would find only scattered pinpricks of other galaxies, each isolated and dim, drifting alone in the gulf. It is one thing to imagine emptiness in human terms, the silence of an empty hall, the stillness of a midnight field. It is another to imagine emptiness on the scale of the universe, where the silence lasts longer than all of human history multiplied a millionfold. The voids are so large that the laws of perspective seem to falter. They cannot be crossed within a human lifetime, nor within the lifetimes of civilizations, nor even within the lifetimes of entire species. They are not just spaces between things. They are worlds unto themselves, defined by the absence of the familiar dot in the language of cosmology. Matter clumps because of gravity. Regions slightly denser than average in the early universe would attract more matter, becoming galaxies and clusters. Regions slightly emptier would lose matter to their denser neighbors. Over time, this process should smooth out the most extreme variations, and yet the voids are not smooth. They are cavernous, their interiors stripped of almost all visible matter. even more unsettling. Some studies suggest that the expansion of the universe proceeds faster inside these voids than in denser regions. This would be consistent with the influence of dark energy, the mysterious force driving cosmic acceleration. But it also raises the question, does emptiness itself play an active role in shaping the universe? The idea that nothing could exert influence is not new. Einstein's own equations describe space as an entity capable of bending and stretching. But here, in the deepest voids, that idea takes on a more literal and haunting form. Regions where the absence of matter may amplify the very expansion of space itself. Humans have long carried a deep, instinctive response to emptiness. The sight of a vast desert, the endless horizon of the sea, or the shadowed depths of a cave can stir both awe and unease. It is the confrontation with scale, the knowledge that within such vastness, the self is infinitesimal. The voids evoke that same response, magnified beyond comprehension. In their presence, even a supercluster of galaxies, containing trillions upon trillions of stars, becomes little more than a fragile ornament on the edge of a great hollow. Standing on Earth, surrounded by light and motion, it is easy to imagine the universe as busy, filled, alive with matter. But from the perspective of the cosmic web, the truth is starker. Most of the universe is not stars or galaxies, but empty space. We are the rare islands in an ocean where the waves are, made of darkness in architectural cathedrals. The strength of the structure lies as much in the spaces between as in the stone itself. The arches and vaults do not merely enclose emptiness. They shape it, give it form, and allow light to pass through in ways solid walls never could. The universe is much the same. The voids are not flaws in its design. They are its structure. The galaxies form the ribs, the filaments, the tracery, but the great spaces between them are what give the cosmic web its scale and strength. Without voids, the distribution of matter would collapse inward. Without the dark, the light would have no contrast in which to shine. It is a strange inversion of human expectation in the grandest architecture of the cosmos. It is the nothingness that defines the form. When the scale and prevalence of these voids became clear, cosmologists were forced to reconsider their models of structure formation. The early universe, observed in the cosmic microwave background, had only tiny variations in density, fluctuations of less than 1 part in 100,000. How could such minor ripples in the early plasma evolve into voids hundreds of millions of light-years wide? Simulations began to show that, given enough time and the right parameters, such structures could indeed form, but the precise distribution and size of the largest voids still stretched the limits of the standard cosmological model. In particular, the very largest voids seemed improbably empty, even in the most extreme runs of the simulations. This mismatch between theory and observation was not enough to break the model, but it was enough to unsettle it, a whisper of something still missing from our understanding by the dawn of the 21st century. The voids were no longer regarded as anomalies to be explained away. They were fundamental to the cosmic story, yet they remained enigmatic, their boundaries well mapped, their interiors poorly understood, their role in cosmic evolution still uncertain. And then, new data brought a fresh surprise. Some of the most extreme voids, supervoids, appeared to correlate with subtle patterns in the oldest light in the universe. This hinted at a possible link between the deepest hollows of the present day cosmos and the earliest moments after the Big Bang. The implication was unsettling. If the largest voids were connected to the initial conditions of the universe, then perhaps they were not just the result of billions of years of gravitational evolution. Perhaps they were imprints, scars left behind by physics we have not yet grasped. The shock of discovery had given way to a deeper tension, the sense that in the silent cathedrals there might be something more than silence. The next step would be to look closer, to peer into the voids with every tool science could muster. Supercomputers would simulate their formation, telescopes would map their faint contents, satellites would study their gravitational imprint on the cosmic microwave background, and with each new investigation, the mystery would grow darker. The voids were not fading into the background of cosmology, they were coming into focus, and what they revealed hinted at forces that might lie beyond even our most ambitious theories. In the early years of cosmic cartography, astronomers worked with maps built from thousands of galaxies. By the dawn of the 21st century, that number had risen to millions, too vast for the human mind to intuitively piece together. The universe's grand design would need to be rebuilt in silicon. Supercomputers became the new ships of exploration, voyaging through mathematical oceans where time could be sped up or slowed down at will. In simulations like the Millennium Run and Illustris, the infant universe seeded with the density variations observed in the cosmic microwave background was allowed to evolve under the pull of gravity and the push of dark energy. What emerged from these digital creations was a revelation. The universe naturally arranged itself into a vast, interconnected web, galaxies clustered along filaments and sheets, flowing like molten glass around immense pockets of empty space. The voids, far from being defects, were a consequence of the same gravitational processes that built the filaments themselves. In these simulations, the voids expanded over billions of years, gently pushing matter toward their edges. The patterns they formed were not random, but the inevitable outcome of cosmic evolution, and yet, some observed voids still seemed too extreme, too sharply defined, to match even the most generous models. While supercomputers painted theories, vision telescopes began delivering the universe in unprecedented resolution. The Sloan Digital Sky Survey mapped over 1 million galaxies, revealing the filaments and voids in the crisp clarity of three-dimensional space. The DESI project, the Dark Energy Spectroscopic Instrument, extended that reach deeper into cosmic history, charting structures billions of light-years away. But even more subtle was the technique of gravitational lensing, the bending of light from distant galaxies as it passes through massive structures. By measuring the distortion patterns, astronomers could map the distribution of matter, both visible and dark. Even in regions with few galaxies, it was lensing that revealed a profound truth. The voids were not truly empty. Invisible scaffolding of dark matter still threaded through them, faint and diffuse, like spider silk stretched to near invisibility. Emptiness, it turned out, was a matter of degree. Inside the voids, matter density dropped to perhaps 1/10 of the cosmic average, sometimes less. What remained was not the dense clumping of galaxies seen in filaments, but a sparse sprinkling of faint, ultra-diffuse galaxies, collections of stars, so spread out that their light could barely be distinguished from the sky's glow. Between these lonely galaxies lay even fainter material, tenuous hydrogen gas detectable only when illuminated by the powerful beams of distant quasars. When a quasar's light passed through a void, astronomers could measure the absorption pattern, a fingerprint of the nearly invisible matter in the emptiness. Perhaps most striking was the realization. that the voids were not featureless hollows. Some contained subtle internal structure, faint, ghostly filaments of dark matter and rare dwarf galaxies, whispering of a complexity even in the deepest cosmic silence. Yet, as data poured in, anomalies emerged. Certain voids appeared larger, emptier, or more sharply bounded than models predicted. One, in particular, the Eridanus supervoid, stood out, not just for its size, but for its apparent alignment with a puzzling feature in the cosmic microwave background, the cold spot. This connection hinted that voids might leave detectable imprints on the oldest light in the universe. An idea with profound implications. If true, it would mean the largest voids were influencing photons that had been traveling for nearly the entire history of the cosmos. Other anomalies defied easy categorization, voids whose gravitational effects seemed too strong for their visible mass, voids appearing in regions where simulations predicted dense filaments. Each discrepancy was a reminder that our models, no matter how sophisticated, were still shadows of the real universe. The cosmic web is not static. Filaments feed galaxies, pulling gas inward, while voids slowly swell, their interiors expanding faster than the denser regions around them. It is a dance of push and pull, shaped by the competing influences of gravity and dark energy. In this dynamic picture, voids are not passive bystanders, but active participants in cosmic evolution. They funnel matter into the filaments and clusters, draining themselves in the process. Over billions of years, they grow larger and emptier, while the filaments grow denser and richer in galaxies. Some cosmologists suggest that studying this interplay, the tension between the expanding voids and the contracting filaments, could yield new insights into the properties of dark energy itself. If dark energy behaves differently in low-density regions, its effects might be amplified inside voids, offering a natural laboratory to test the most elusive force in physics. In the simulated universes of supercomputers, one can drift into a void and watch it evolve over billions of years in minutes. Galaxies move apart, faint gas clouds thin into near invisibility, and the dark matter scaffold stretches ever wider. The edges become more defined as surrounding filaments tighten their grip on infalling matter. The silence of such a place is conceptual rather than literal, for there is no air to carry sound, but the absence of events is almost tangible. In a void, the timescales of change are measured not in millions, but in hundreds of millions of years. Even light itself takes geological ages to bring news from one edge to the other. What the simulations cannot convey, however, is the philosophical weight of such emptiness, the realization that these hollows make up the majority of the universe's volume. The places where galaxies and clusters reside, where stars burn and planets orbit, are the exception, not the rule. By the second decade of the 21st century, the cosmic web had been mapped in greater detail than ever imagined. The voids had names, sizes, shapes, and densities catalogued with care. Yet the deeper the view, the more urgent the questions became. If the voids were merely the natural gaps between filaments, why did some of them bear the hallmarks of deeper, stranger processes? Could the anomalies hint at new physics, unaccounted for, matter, or even relics from the earliest instance of cosmic inflation? To answer these questions, astronomers would need to do more than map. They would need to correlate the largest voids with the universe's oldest light, to detect their gravitational fingerprints in the cosmic microwave background, and to measure how their interiors were expanding in real time. The investigation was no longer about whether voids existed. That was settled. It was about what they were telling us about the universe's hidden architecture, and the clues, it seemed, pointed toward a mystery larger than the voids themselves. Beyond the already staggering scale of the known voids lay the so-called hollows so immense they seemed to touch the limits of cosmic structure itself. Some appeared to align with anomalies in the oldest light in the cosmos. Others seemed to grow faster than the universe's average expansion. The next step in the investigation would lead scientists directly into these vast abysses, where the emptiness might hold not only the memory of the early universe, but also the fingerprints of forces yet unknown. The map was complete enough to navigate. The time had come to descend deeper into the hollows, and into the cold spots where the voids seemed to whisper to the cosmic dawn. In the southern sky, beyond the curling line of the constellation Eridanus, lies a darkness stranger than most. To the human eye, through even the best telescopes, it appears no different from any other corner of the heavens, a scatter of faint galaxies on a canvas of black. But to astronomers mapping the universe in 3 dimensions, it revealed itself as something remarkable. One of the largest known voids in the cosmos, the Eridanus supervoid, spans nearly 2 billion light-years in length. Its interior is not completely empty. A handful of galaxies drift within it, faint and far between, but its density is so low that it stands out even in a universe dominated by emptiness. What made it more than a curiosity was its unexpected link to an ancient whisper, the cosmic microwave background, the afterglow of the Big Bang. In that afterglow lies a patch known as the cold spot, a region slightly cooler than the surrounding sky, puzzlingly large and pronounced. The possibility arose that the Eridanus supervoid, sitting in the same direction as the cold spot, might be responsible for its chill. If true, the connection would be an example of the integrated Sachs-Wolf effect. As light from the cosmic microwave background passes through a large gravitational well or void, the stretching of space can slightly alter its energy. In the case of a supervoid, the accelerated expansion of space within it could leave the photons with a net loss of energy, cooling them by a tiny fraction of a degree. The concept was elegant, a vast emptiness casting a shadow, not in light, but in temperature, across the oldest radiation in the universe. The effect is subtle, measurable only in microkelvins, yet on the grand scale of the cosmic microwave background, such differences are significant. If the cold spot were indeed the fingerprint of the Eridanus supervoid, it would mean that events in the present-day universe could leave marks on relic light that has traveled for nearly 14 billion years. But the story is not so simple. Calculations suggest that even a supervoid as large as Eridanus should not produce a cold spot of the observed magnitude. The alignment may be more than coincidence, but the void alone seems insufficient to account for the full effect. This discrepancy leaves open the possibility that something else is at work, something beyond our current models. Could there be multiple overlapping voids along the same line of sight, their effects combining? Could the cold spot be a remnant of an early universe anomaly, such as a texture or defect left from cosmic inflation? Or, more provocatively, could it be the mark of a collision with another bubble universe, a domain with different physical constants, brushing against our own in the deep past? The Eridanus supervoid is not alone in stretching the limits of what cosmologists expect. Other discoveries have revealed structures so large they push the boundaries of the cosmological principle itself. The Oculus Corona Borealis Great Wall, for example, is a filamentary complex of galaxies and clusters spanning over 10 billion light-years, a scale so vast that it approaches a tenth of the observable universe. If confirmed in full, it would be difficult to reconcile with the idea that the universe is homogeneous on its largest scales. These megastructures and supervoids are two sides of the same coin, the brightest walls and the darkest hollows of the cosmic web, both hinting at patterns beyond the smooth averages our theories assume. Their very existence forces astronomers to ask, are we seeing statistical flukes, or signs that our understanding of cosmic evolution is incomplete? One of the most striking observations about voids is their tendency to grow. In the standard picture, as galaxies and clusters pull together into denser regions, the spaces between them expand more rapidly. Over cosmic time, the voids not only grow in volume, but also become emptier, as matter is funneled away toward the surrounding filaments in regions dominated by dark energy. This process may be even more pronounced. Some simulations suggest that the rate of expansion inside the largest voids could exceed the cosmic average, accelerating their growth. If so, the largest supervoids we see today are the ancestors of even greater hollows in the far future. Cathedrals whose arches will stretch until their walls disappear beyond the horizon. This raises a profound possibility that the cosmic web itself may be a temporary structure. In trillions of years, the filaments could thin into obscurity, leaving only the faintest embers of galaxies scattered across an ocean of almost perfect nothingness. To study these extremes, astronomers are now combining multiple techniques: redshift mapping, gravitational lensing, and microwave background analysis to probe voids at the limits of detection. In the case of the Eridanus supervoid, future observations aim to map its interior in greater detail, searching for faint galaxies and hidden gas. High-resolution CMB studies may reveal whether its alignment with the cold spot is coincidence or causation. For other supervoids, researchers are examining how they distort the light of more distant quasars, a method that can yield clues about the dark matter within them. The results could confirm whether the largest voids are merely statistical outliers, or signposts pointing toward physics yet undiscovered. By now, the voids are no longer mere absences. They are recognized as dynamic components of the cosmos, shaping light, structure, and even time's flow in their silent interiors. The cold spot connection suggests that these vast hollows can bridge the gap between the universe's earliest moments and its present-day structure. But every explanation seems to lead to deeper questions. If supervoids can influence the oldest light in the universe, what else might they reveal about the conditions of the early cosmos? Could they be the fossilized outlines of quantum fluctuations stretched across billions of light-years by inflation? Or could they be boundaries, the edges of cosmic domains in a larger multiverse? In these possibilities lies both the allure and the danger of speculation, the temptation to see in the voids not just absence, but purpose. The investigation into the cold spots and supervoids does more than deepen the map of the universe. It stretches the boundaries of the known. Each measurement, each simulation, draws us closer to the edges of our cosmological model, where the data no longer fits neatly and new theories begin to whisper. From here, the path forward leads into the realm of speculation. If the voids hold secrets that standard physics cannot fully explain, then perhaps their dark interiors are not just empty expanses, but windows into forces and dimensions we have yet to imagine. It is into this territory that science now steps, carrying its most daring questions. What are these voids made of? What shaped them? and in their silent halls is the universe hiding the keys to its own fate. In the prevailing cosmological model, the lambda cold dark matter paradigm, or CDM, the universe began with quantum fluctuations magnified by inflation. The violent expansion that occurred a fraction of a second after the Big Bang. These ripples in density were minute, barely 1 part in 100,000. Yet over billions of years they became the scaffolding for all cosmic structure. Gravity pulled matter into denser regions, building galaxies and clusters along filaments, while less dense regions emptied further, forming the voids. The pattern, when simulated on supercomputers, produces a cosmic web much like the one we observe today. In this view, voids are not mysterious anomalies. They are the natural negative space in the universe's architecture, the spaces between the ribs of the cosmic cathedral. Their size and shape reflect the interplay of gravity, dark matter, and dark energy over cosmic time. Yet, even within the CDM framework, certain voids stretch the limits of expectation. Some are emptier, larger, or more sharply bounded than the model predicts. For these, orthodoxy offers no immediate answer. One hypothesis focuses on the role of dark energy, the unknown force driving the accelerating expansion of the universe. In standard theory, dark energy acts uniformly, affecting all of space equally. But what if it doesn't? If dark energy interacts differently in low-density environments, its influence inside voids could be stronger than in denser regions. The result, an accelerated local expansion, making the voids grow faster and emptier than expected. In this scenario, voids become not just passive gaps, but active engines of cosmic evolution, expanding bubbles in the foam of the universe, pushing galaxies farther apart and subtly reshaping the web. If measurable, such an effect could offer one of the clearest windows into the true nature of dark energy. Beyond the standard model lie ideas more speculative. Some physicists have proposed that voids might be scars from topological defects in spacetime, relics of phase transitions in the early universe, when fundamental forces separated and cooled in the extreme conditions of those first instants. Spacetime itself may have contained imperfections, cosmic strings, textures, or domain walls. Over billions of years, these defects could have left vast imprints on the distribution of matter, carving out regions of anomalous density that became the great voids we see today. Though no direct evidence for such defects has been found, the voids remain tempting candidates for their fossil tracers. A single confirmed detection would rewrite the history of the universe's first seconds. The most audacious theories look beyond our own universe entirely. In some models of inflation, our cosmos is just one bubble in a vast multiverse, a foam of universes, each with its own physical constants and perhaps even different laws of physics. If two such bubbles ever came into contact, the collision could leave a lasting mark, a boundary zone where the properties of space subtly shift. On a cosmic map, such a scar might appear as a supervoid, a vast, oddly uniform hollow, with galaxies at its edge behaving differently than expected. This idea has been invoked, cautiously, to explain certain anomalies, including the cold spot. While no consensus exists, the prospect that some voids could be the footprints of other universes remains one of the most haunting possibilities in cosmology. There is another possibility, darker still. Our universe, according to quantum field theory, may be in a false vacuum state, stable for now, but not truly the lowest possible energy configuration. If so, it could, in principle, tunnel to a lower energy state. changing the very structure of physics itself. This decay would expand outward at nearly the speed of light, rewriting the laws of nature as it went, a transformation impossible to see coming and impossible to survive. Some speculative scenarios imagine that such a transition might begin in a remote region of space, leaving behind an expanding sphere where the old vacuum is gone. To an observer in our universe, such a region might resemble an unusually large, unusually clean void, though in reality it would be far more than emptiness. There is no evidence for such an event in our cosmic neighborhood, yet the concept lingers, a reminder that the universe's stability rests on assumptions we cannot yet prove. Astronomers are now using machine learning to search for subtle patterns in the arrangement of voids. If these patterns match the predictions of certain exotic theories, specific size distributions, alignments, or correlations with background radiation, it could point the way to new physics. For example, if voids are influenced by variations in dark energy, they might show characteristic shapes or rates of expansion. If they are relics of early universe defects, their distribution could reveal the symmetry-breaking events that shaped them. If they are multiverse boundaries, their edges might host unusual galaxy properties or gravitational effects. At present, the data is tantalizing but inconclusive. The cosmic web is vast, and its voids are many. Teasing out the signature of a single process requires precision beyond even our current surveys. Yet with each year, the resolution sharpens in the end. The voids stand at the boundary between what science can explain and what it can imagine. They are testbeds for our most precise theories, yet also mirrors in which we glimpse our boldest speculations. In their emptiness, they force a question. Is the universe's architecture simply the outcome of gravity and expansion, or is it also shaped by events and forces from epochs we have yet to understand? Physicists tend toward caution, but in quiet moments the mind wanders to the possibility of hidden walls between universes, two scars left by primordial events, to the notion that nothingness itself might be a dynamic, shaping force. For all the theories, the voids remain elusive, the data is fragmentary, the models incomplete, the truths hidden in Hollow's light takes eons to cross. And so, science turns to its instruments, to telescopes, satellites, and detectors to push deeper into the darkness, seeking the faintest signs of what the voids are made of, and what they may become. The cathedral has been mapped, its arches traced in galaxies and gas. But to know its purpose, we must explore its silence, to listen for echoes in the darkness, where the next answers may already be waiting. In the search for answers, science turns to its instruments, the eyes and ears of humanity, reaching far beyond the limits of flesh and bone. Over the past 2 decades, a new generation of telescopes and surveys has begun to probe the voids with unprecedented precision. At the forefront is DESI, the dark energy spectroscopic instrument mounted on the Mail 4-meter telescope in Arizona. DESI's mission is to measure the spectra and redshifts of over 40 million galaxies and quasars, mapping the universe's large-scale structure with extraordinary detail. Each spectrum adds another point to the cosmic atlas, tracing the edges of filaments and the depths of voids. Alongside it, the European Space Agency's Euclid mission, launched to study dark energy and dark matter, is charting both visible and invisible structures. Euclid's wide-field view allows it to capture the geometry of the cosmic web over vast swaths of sky, mapping not only galaxies, but also the gravitational fingerprints of unseen matter. Then there is the Vera C. Rubin Observatory's legacy. Survey of Space and Time, LSST, poised to collect over 20 terabytes of data every night for a decade. With its wide field and rapid cadence, LSST will record billions of galaxies, revealing the cosmic web in a dynamic new light and allowing astronomers to track how voids evolve over time. Of all the techniques for studying voids, perhaps the most powerful is weak gravitational lensing. It is an effect so subtle that it cannot be seen with the naked eye, yet it bends our understanding of the universe. Light from distant galaxies is minutely distorted as it passes through gravitational fields. In dense regions, this distortion is strong. In voids, it is delicate but measurable, revealing the presence of diffuse dark matter even in places where no galaxies shine. By stacking thousands of voids together in a statistical sense, astronomers can detect their average lensing signal. This allows them to infer the distribution of matter inside the voids, test models of dark matter's behavior in low-density environments, and search for deviations that could hint at new physics. Weak lensing turns the voids into laboratories, silent but filled with invisible mass, each one a test of the laws that govern the cosmos. Another method comes from the brightest beacons in the universe, quasars. These luminous cores of active galaxies, powered by supermassive black holes, can outshine their host galaxies by factors of thousands. Their light, often emitted billions of years ago, serves as a backlight for the structures it passes through. When quasar light traverses a void, it is subtly altered. Intervening clouds of hydrogen gas absorb specific wavelengths, leaving behind a pattern known as the Lyman alpha forest. In dense regions, the forest is thick with absorption lines. In voids, the pattern thins to near transparency by comparing quasar spectra along different lines of sight. Astronomers can map the distribution of gas within voids, gas so diffuse it could never be seen directly. These measurements complement lensing studies, filling in the picture of what truly lies inside the cathedral's vast, dark chambers. The sheer volume of modern astronomical data is beyond the capacity of human analysis alone. Machine learning algorithms now sift through petabytes of survey data, identifying voids, classifying their shapes, and flagging anomalies for further study. AI can detect patterns invisible to the eye, correlations between void size and surrounding, filament geometry, or subtle asymmetries in galaxy distributions that may point to dynamic processes within the void. In some cases, algorithms have uncovered potential void alignments, chains of hollows that may trace larger superstructures, or perhaps even relics of early universe processes. While these findings remain tentative, they hint at the possibility that voids are not isolated features, but parts of grander cosmic patterns. The tools we have today are powerful, but the instruments of tomorrow promise a revolution. Planned observatories such as the Nancy Grace Roman Space Telescope will combine deep imaging with wide-field spectroscopy, allowing for simultaneous mapping of galaxies and dark matter. The Square Kilometre Array, the largest radio telescope ever built, will map hydrogen gas across billions of light-years, tracing the faint structure of the cosmic web even where galaxies are absent. By capturing the distribution of matter inside voids at radio wavelengths, it will provide an entirely new perspective on their contents and dynamics. Even gravitational wave observatories may play a role. In principle, the stretching and squeezing of space caused by passing gravitational waves could be influenced by the large-scale structure they move through, including voids. While such measurements are far beyond current sensitivity, they remain part of the long-term vision for probing the cosmic web in every possible way. Each of these tools is more than just a way to measure distances or densities. They are tests of theories about dark energy's variability, about exotic early universe physics, about the very origin of cosmic structure. All make predictions about the properties of voids. By comparing simulations under different theoretical assumptions with actual observations, cosmologists can rule out entire classes of models. For instance, if void expansion rates differ from predictions, it could indicate that dark energy behaves differently in low-density regions, a finding that would reshape cosmology. Similarly, if void shapes or alignments match patterns predicted by exotic physics, such as cosmic textures or multiverse collisions, it would point toward events in the earliest fractions of a second after the Big Bang. The voids, in this way, are not empty canvases, but records of the universe's deepest history. Studying voids is, in a sense, like listening for echoes in a cathedral. The vast space does not produce sound itself, but it shapes and amplifies what passes through it. In the cosmos, the echoes are the subtle imprints voids leave on light, matter, and radiation. The cosmic microwave background, the distribution of galaxies, the lensing of distant light, the absorption lines in quasar spectra, all carry the faint signatures of voids. By detecting and decoding these signatures, astronomers hope to reconstruct not only the present state of these hollows, but their origin stories. This work requires patience on a cosmic scale. Mapping a single void in detail can take years of observation and analysis. Understanding their collective behavior may take decades. Yet the reward could be nothing less than a new understanding of the universe's architecture, and perhaps of the forces that built it. With each new measurement, the voids become more than empty shapes on a map. They become places, regions, with internal structure, histories, and roles in the cosmic drama. They are no longer passive gaps, but active participants in the unfolding story of the universe. And yet, for all the data, they remain places of profound mystery. The numbers and maps cannot capture the experience of contemplating their scale, their stillness, their place in the cosmic web. For that, science must turn, as it always has, to philosophy. The final step in this journey will not be taken with telescopes or simulations, but with reflection, asking what it means for humanity to exist in a universe where most of the volume is not filled with light and matter, but with silence. In the language of human experience, emptiness is absence, a room without furniture, a field without trees, a street without voices. It is defined by what is missing, and it is temporary, a void waiting to be filled. But in the universe, emptiness is not absence, it is architecture. The great hollows of the cosmic web are not waiting for matter to come. They are the shape that matter makes when it arranges itself according to the rules of gravity, expansion, and time. Here, in the depths of a cosmic void, there is no sense of incompleteness. The cathedral is not unfinished. Its nave was always meant to be open. The darkness is not a flaw. It is the space in which the light can exist. The arches of emptiness are as much a part of the structure as the filaments of galaxies that frame them. In the medieval cathedrals of earth, stonemasons worked for generations to raise walls, buttresses, and spires. They carved each arch, knowing they might never see the final vault completed. The universe has no such artisans, yet it has built something far greater. The filaments and voids together form a structure that spans the visible universe. In this architecture, the walls are clusters of galaxies, the buttresses are filaments of dark matter, and the nave, the open hall, is the void. And unlike human cathedrals, these were not built in decades or centuries, but in billions of years. From the outside, the structure is invisible. Only through maps, simulations, and the slow accumulation of light from distant galaxies does the pattern emerge. And once seen, it changes the way the cosmos is understood, not as a random scattering of matter, but as a deliberate arrangement carved by time itself. Earth is not at the center of this cathedral, nor is the Milky Way. Our galaxy lies along, a filament pressed against the edge of a smaller void, the local void whose interior stretches for tens of millions of light years. If the local void were entirely empty, its gravitational imbalance would pull the Milky Way subtly outward, away from its center. In reality, even a void's interior contains faint matter and hidden galaxies, but the effect is still measurable. We are not fixed in place. We drift along the currents between hollows. This position on the thin ridge between emptiness and structure is not unique to us. Most galaxies occupy similar margins, clinging to the edges of voids. The bulk of the universe's matter is gathered in these filaments, leaving the vast central volumes of the voids almost untouched. To live on the cosmic shore is to be bound to the coastlines of existence. Looking out over an ocean we can never sail, because it is not made of water but of geometry and time. Every point in the observable universe is surrounded by voids. If we could travel far beyond the reach of current maps, the pattern would repeat. Filaments of galaxies framing hollows of space, again and again, like the unending tracery of a cathedral's ceiling. Beyond the observable limit, beyond the horizon set by the speed of light and the age of the universe, the pattern may continue forever. Or it may change, shaped by physics we cannot yet imagine. The shoreline of the cosmic sea is infinite, and we see only a small curve of it. In this way, the voids are reminders of our cosmic limitations. We cannot cross their interiors in any human timescale. We cannot see beyond the horizon that expansion has drawn around us. We can only measure, model, and imagine. Yet, in this imagining lies one of humanity's greatest strengths, the ability to give meaning to what is beyond reach. In the vast halls of the voids, galaxies are rare. A lone spiral may drift for billions of years without ever encountering another of its kind. Its stars are born, live, and die in isolation. Its light, when it escapes, travels unhindered for unimaginable distances before brushing against the lens of a telescope. These galaxies are like candles in a cavern, each one surrounded by darkness so complete that the light seems impossibly fragile. Yet their existence proves that even in the deepest emptiness, matter can gather, stars can form, and light can shine. For civilizations, if they exist in such lonely places, the night sky would look almost empty. A few smudges of starlight, a scattering of faint points, and then the endless black. The idea that such civilizations could share the same universe as ours, with our rich, crowded Milky Way sky, is a reminder of the diversity of cosmic experience. In human history, emptiness has often been feared. The blank spaces on ancient maps were filled with monsters, the deserts were thought to be cursed, and the depths of the ocean were seen as places of danger. Yet again and again, humanity has ventured into the empty spaces and found them to be not curses, but opportunities frontiers, that revealed more about the world than the familiar ever could. The voids are the ultimate frontiers. They cannot be crossed in lifetimes, or even in the lifetime of species, but they are part of the same universe that gave rise to us. They remind us that our home is an oasis, a rare cluster of light in a sea of dark. They remind us that rarity can be precious and that life fragile. Improbable life can exist in a universe where most places are barren. Imagine standing inside one of these cosmic cathedrals. There is no floor, no ceiling, no air. Only the black expanse stretching in every direction. Far at the edges, the faint arc of a filament glows. A chain of galaxies, each one a city of suns. Between you and that distant light is nothing that human senses can perceive. You are not standing still. Space itself is carrying you outward, away from the edges, into deeper darkness, and as you drift, the cathedral grows. The arches stretch. The silence deepens. It is in this silence that the universe keeps its oldest secrets, not in the bright hearts of galaxies or the violent collapse of stars, but here in the spaces between, spaces that are not empty after all, but filled with the structure of absence, th,